Right now, a block of ice and rock is tearing through our solar system. It arrived from deep space, and based on its chemical signature, it formed up to 12 billion years ago, making it nearly as old as the universe itself. We are used to comets in our neighborhood. There are billions of them residing in the Oort cloud at the very edge of our solar system. Though they orbit at extreme distances, they are permanently bound by our sun's gravity. But this object, named 3I Atlas, is a rogue. It formed around an entirely different star, was violently ejected from its home system, and has been wandering the interstellar void ever since. Catching a rogue comet as it passes by offers an incredibly rare opportunity. It gives us a direct physical sample of an alien star system, allowing us to study the building blocks of another world without having to leave our own. To know for certain that an object is an interstellar visitor, astronomers look to orbital mechanics. Local bodies follow closed, elliptical paths around the sun. An outsider will betray its origin by following a path that the sun's gravity cannot contain. This diagram shows the inner solar system and the trajectory of 3I Atlas. Notice how the comet's path forms an extreme, open-ended curve slicing through the inner planets. This is a hyperbolic orbit, and 3I Atlas has an eccentricity of 6.14, the highest ever recorded. That high eccentricity is driven by extreme speed. The comet is moving at roughly 34 kilometers per second relative to the sun. At that velocity, our star's gravity simply cannot pull it into a stable orbit. 3I Atlas is acting like a bullet shooting straight through the planetary plane. It will make one rapid pass around the sun before plunging back into interstellar space, giving researchers a very short, strict window to analyze it. Our first confirmed interstellar visitor, Oumuamua, was relatively quiet and rocky. 3I Atlas, by contrast, is a highly active comet. As it approaches the heat of our sun, its surface is violently boiling off. To capture this activity, astronomers pointed orbital observatories, like the Hubble Space Telescope, directly at the comet as it closed in on perihelion, its closest approach to the sun. Hubble revealed strange physical anomalies. The comet was wrapped in a massive, teardrop-shaped dust cocoon, firing prominent jets of gas directly toward the sun. Other spacecraft, like the Jupiter-bound JWST probe, captured additional imagery. They found the comet trailing a distinct plasma tail, formed by ionized gas, accompanied by a fainter, structurally unusual dust tail. This intense outgassing is exactly what scientists hoped for. The solar heat was effectively ripping the comet open, venting its deep internal ice out into space, where our instruments could read its chemical signature. The gas venting from 3I/Atlas contains a bizarre chemical cocktail. It is completely dominated by carbon dioxide, and it contains high amounts of atomic nickel vapor, a heavy metal we rarely see venting this far out in our own system. To understand what this means, researchers turned to large radio telescopes on Earth to analyze the specific molecular structure of the comet's water. They were looking for deuterium, a heavy isotope of hydrogen that contains an extra neutron. Observations showed the water inside 3I Atlas holds an incredibly high concentration of it, nearly 1%. That's roughly 30 times higher than local comets. The laws of physics dictate how deuterium behaves. Reactions only lock these high concentrations into water ice when the environment drops below 30 Kelvin, or minus 243 degrees Celsius. Because that specific deuterium ratio is permanently frozen into the comet, we know 3I Atlas was born in a molecular cloud far colder than the stellar nursery that forged our own solar system. The strangest discovery came when researchers looked at the comet's carbon. 3I Atlas is almost entirely depleted of the isotope carbon-13. This graph maps the galactic timeline of carbon-13. Synthesized inside dying stars, its concentration steadily builds up over time. Because 3I Atlas lacks it, it formed before the Milky Way was enriched. Astronomers placed the comet's accretion at 10 to 12 billion years ago. We can trace the comet's incoming velocity back to a region called the Milky Way's This disk. This is a deep, ancient layer of the galaxy, populated by old, metal-poor stars. At 12 billion years old, 3I Atlas was fully formed and drifting through the interstellar void for over 7 billion years before our sun even ignited. Previously, models of planetary formation suggested that the early metal-poor environments of the ancient galaxy lacked the heavy elements necessary to efficiently build complex, volatile-rich planetesimals. 3IAT Atlas proves that assumption wrong. The comet is packed with water ice and prebiotic organics like methane and formaldehyde. This confirms that the machinery of planet formation was already highly active during the galaxy's cosmic noon, heavily producing complex chemistry in a metal-poor era. To deliver this data, the comet survived an ejection from its host star, navigated chaotic gravitational fields, and crossed unimaginable distances of the Milky Way over 12 billion years, arriving right as our telescopes were sensitive enough to see it. The parent star that birthed 3I-ATLS is likely long dead, but as this frozen time capsule speeds out of our solar system and disappears back into the dark, it leaves us with a direct, physical link to the dawn of the universe. If you want to keep exploring the outer edges of space and the deepest mysteries of our galaxy, hit subscribe and we'll see you in the next video.